Now we are ready to focus the discussion on the flowchart production system. The flowchart is look like the continuous process because they produce in mass, they produce in large volume. But the differences of these two systems, as I told you earlier, is that the end product of the flowchart is discrete, but the continuous process always produce uh, the, the, the product that is naturally uh, indivisible, okay, or the fluid. And for the flowchart, okay, so the flow, the material flow or the part flow of the flowchart is unidirectional. It means that the, the routing is like this from the raw material to work in process and to finished good, like this. They have to go to machine number 1, 2, 3, 4 and then go out. And normally for the flowchart, they use automated special purpose equipment to produce high volume, low variety of the product or mass production. And sometimes it's called the assembly line, okay, production line or assembly line. This is the picture that I have already mentioned about the typical flowchart, right? We have another kind of flowchart. We call it a generalized flowchart. It means that some of the process could be skipped by a certain product. For the typical flowchart, the part need to go through the whole process from workstation number 1, 2, 3 and then going out. But for the generalized one, some part could be skipped. Some workstation could be skipped, like this part may require just the workstation number 2 and 3 and go out, or this part could require just workstation number 3. Alright, okay, this is the generalized flowchart system. But for the typical one, the part or the raw material need to go to the whole process from machine 1 or from the starting process till the end of the process to become the finished good. The example of the flowchart in terms of manufacturing, maybe automobile industry, pencil manufacturing or steel making. For the service industry, like process insurance claim, bill payment at the counter service, or processing ID card. The advantage of the flowchart, as I told you earlier, the flowchart always focus on high productivity, so they gain the low unit cost. So they gain the low unit cost by using the specialized high volume production equipment, so that they can produce in mass with low cost. And because they produce in mass, so they normally purchase the raw material in bulk, so they can negotiate with the supplier to reduce the price of the raw material. And because labor need to do nothing apart from load and unload operation to the machine, so they need low skill worker, so the rate, the labor rate, okay, of the worker is low. Field supervisor, less wages for the labor. And because they produce the standardized product, so low inventory, low in process inventory, and their production lead time could be easily determined because the standardized operation, so that you can estimate the total production lead time very easily, and very simple management and control, and more reliable delivery date. But the disadvantage of the flowchart could come from because the flowchart focus on productivity. So if you want to change the variety of the output, it's going to be very difficult because you use the specialized equipment, right? For the specialized equipment, you cannot easily change to produce more or to produce more variety of the product. And again, difficult to change the rate of the output, and minor design change could require substantial change in terms of the equipment and in terms of labor, because they do just load and unload operation, so they may feel bored and absent from work. And work is not very challenging since the equipment perform skill tasks. And the last one is vulnerable to equipment breakdown. Show you the picture. Because the flowchart process must come from the first operation and second and third, and then at the end, okay, the final operation like this one. So if this machine break down, the whole line would be stopped. So it is very vulnerable to machine breakdown, and one machine breakdown could bring about the whole line stop. So it's not very good in terms of the reliability of the system. And there another disadvantage of flowchart that could be raised is difficult to dispose or modify special purpose equipment, large support staff required to keep the line running smoothly. In terms of the installation or initial setup of the system, it is very complex, and to gain high efficiency, our machine must be work at the same pace or coordinate the operation, or you need to do the line balancing, which I'm going to tell you later in this course. In order to design the flowchart, okay, the objective of the flowchart design is to assign tasks to several workstations. Sometimes this problem is called assembly line balancing problem, so that you could obtain smooth utilization of machine or worker, and you could be able to identify the bottlenecks machine. Two kind of the flowchart that you could come across. The first one, we call it pace line. For the pace line, normally we have some sort of conveyor to move the output along the line at the constant rate. And whenever the operator do the job and finish the job, they put their finished part into the conveyor, and the conveyor will move the part. Okay, so the movement of the part will be constant, right? So you can see that in the automobile assembly line. Sometimes the worker could stand in the conveyor and move along with the conveyor, and then once they finish the operation, they have to walk back to the starting workstation again, right? That is the pace line. So for the pace line, they need some conveyor to move the output. But for the unpaced line, okay, the way that they control the pace of the system is by the worker themselves. Okay, so the worker build up a queue between machine and themselves, and then they can vary their working speed to meet the need of the job or their personal need. So meaning that you can see here they have some sort of buffer. So if they see that, if this worker seeing that this worker still cannot send them the work, they can lower their speed. He can lower his speed, right? And whenever he see that his input buffer is high, they can increase his speed to produce more part. So the way they control the speed of the line is by themselves. No conveyor at all. So this is what we call unpaced line. Okay, we come to the line balancing problem. So please pay more attention on this on the slide on this slide. The cycle time, okay, the definition of the cycle time is the time that each workstation must complete its task. At the end of this time, every workstation must pass on to the next workstation. It means that, okay, we have the cycle time to control the movement of the part. At the end of this time, the worker needs to send part to the next worker. So the calculation of the cycle time could be the equal to the available work time divided by demand. The available work time here, you need to, this is the actual available work time. So if you have the 24 hour, you need maybe sorry, if you have 8-hour shift for work, and you may have 1 hour break for lunch, so the available work time, the available work time supposed to be 8 minus 1, which is 7 hours. Alright, so this is the actual available work time. Please remember that. And this is the demand. So the theoretical number of workstation, okay, this theoretical T here stands for theoretical, N is the number of workstation. Theoretical number of workstation is equal to summation of task time divided by cycle time. And the efficiency of the system is equal to output divided by input, and equal to the total task time. Okay, total task time is equal to the summation of task time divided by nx station multiplied by cycle time. Nx could be theoretical number of workstation or actual number of workstation. If it is theoretical number of workstation, efficiency is the theoretical efficiency, and if it is the actual number of workstation, this one is going to be actual efficiency. I will show you how to calculate it later. Okay, suppose in this example we want to do the line balancing. We want to decide the flow shop which operate one shift per day. One shift is equal to 6 multiplied by 60 multiplied by 8 hours, 60 minutes multiplied by 8 hours, okay, which is 480 minutes. And this company received 1,200 credit application per day and must complete all the job in a day. So the cycle time of this line, in order to complete the whole application within a day, could be the available work time, that is 8 multiplied by 60 and divided by 1,200. 8 hour day, 1 hour is equal to 60 minutes, and this is the requirement, right? 1,200. So the cycle time of the line, okay, is equal to 0.4 minutes per application. 0.4 minutes per application. What if the cycle time of the line is more than 0.4, like 0.5, 0.6, 0.7? In that case, the application, 1,200 application that are required cannot be complete within a day. What if the cycle time of the line is lower than 0.4, like 0.3, 0.2, something like that? It means that the whole operation to produce 1200 application could be finished earlier, right? Okay, please pay attention to the calculation and the concept of the cycle time. Please remember that at the end of this cycle time, or at the end of the 0.4 minute, every worker who work in the line must send their finished job to the next worker every 0.4 minute, right? Okay, so every cycle time, the worker, at the end of the cycle time, every worker have to send their work to the next workstation. And if you can calculate the cycle time, then NT, number of workstation here, total task time divided by cycle time, task time, cycle time, you get cycle time here. Okay, so task time here, suppose that we have, in order to process the application, we have 7 tasks to do, right? Each task, they have their operation time or time required to complete the task. Like task A require 0.2 minute, task B require 0.37 minutes, and the total task time 1.9 come from 0.2 plus 0.37 plus 0.21 until plus 0.36, we got 1.9. Alright, okay, this is going to be used in the theoretical number of workstation. So you got sigma task time of 1.9, and then you divide by the cycle time, you get the theoretical number of workstation of 4.75. Always round up, so the theoretical number of workstation is going to be 5 workstation. Even though you got 4.1 or 4.01, the required number of workstation in theory, so you get 5. Always round up. Okay, theoretically you need at least 5 workstation to do the job. Alright, okay, so you got 7 tasks, you got the time required to complete the task, but the task has the preceding task to complete. So in this case, task A, no preceding task, but in order to produce task B and task C, okay, you need to complete task A first, task D as well, right? B, C, D, you need to complete A. Task E, before it can be started, task C and D must be finished. Task F, you need to finish task B and E. And task G, before it could be started, you need to finish part F. So you need to draw a precedent chart or precedent graph for the credit for this application like this. So first of all, you need to you need to find the task that come without the preceding task. Okay, in this case we got just only task A. So you put task A here, right? And you put the required time for task A, that is 0.2. Okay, 0.2. And then task B, C, and D could be start if or whenever task A finish. So here, task B, task C, and task D. A finish, task B. A finish, task C. A finish, task D. And this is the operation time for B, C, and D. And then task E requires C and D. E requires C and D. And then task F require B and E. Task F require B and E. And finally task G require F, like this one. So you need to draw this graph, okay, in order to show the precedent relationship between different tasks. It means that whenever you need to allocate tasks to the workstation, it must not violate the precedent relationship. Okay, so whenever you want to allocate tasks to workstation, you need to come back to this one to check whether or not it's violate the precedent relationship. Okay, and the efficiency in terms of the theoretical of 5 workstation, we got 5 workstation here, right? Okay, so the efficiency is the output divided by input of 5 workstation, that is total task time divided by the theoretical number of workstation multiplied by cycle time. You got total task time is 1.9 multiplied by 100 because you need to convert into percent, and number of theoretical number of workstation, which is 5, and the cycle time, which is 0.4 from your first calculation here. And then you got efficiency, theoretical efficiency, you got 95% here. And then in order to allocate tasks to workstation, or in order to form the line, you need to select the operation to fill in, okay, to fill in the workstation. So there are plenty of rules that you can use, but one of the simplest rule and it's work quite effectively, that is LOT rules. Okay, LOT stands for longest operation time. You select an eligible task. Okay, there will be several tasks, but you have to consider just eligible tasks with the longest operation time first. Okay, I will show you how to do it. Okay, first you need to form a table, okay, which the table heading consists of station, available time, eligible task, and then select task and the idle time here. First you need to open the first station, okay, the first station, number 1. Since the cycle time is equal to 0.4, right? Okay, the maximum time that each workstation could use is equal to the cycle time. So the available time of each station at the beginning is always 0.4 here, right? Okay, this is the starting from the cycle time. And then looking at the precedent graph, you need to find the eligible task, okay, that is not violated the precedent relationship. In this case, just only task A could be start, right? Because they have this task has no precedent task. Okay, so in that case, you put eligible task A here, and so you select it or not. It depends on the time requirement of task A. Because task A requires 0.2, the available time is 0.4, so 0.2 could be is less than the available time, so task A could be allocated in workstation A. So you select task A to allocate in workstation A. And the idle time here, okay, idle time come from the available time 0.4 minus the time of task A, the operation time of task A, that is 0.2, which is 0.2. 0.4 minus 0.2, which is 0.2 here. And then the idle time means that this is the still remaining time of the workstation A. The remaining time of workstation A, you move it to here, available time of workstation A. And because you have already done A, so in that case, the eligible task is B, C, and D, right? B, C, and D. So you put the eligible task in here, B, C, and D. Which one would you select? Okay, which one would you select? It depends on which one could fit But in order to select the eligible task, you need to use the LOT, longest operation time first. The longest operation time of B, C, and D is B, right? That is 0.37. But your available time is just 0.2, so B cannot be fit in because it's greater than 0.2. You move to the next one, next longest one, right? That is C, 0.01. 0.21. 0.21 is still more than 0.2, so C could not be selected. So you move to the last one, that is 0.18. 0.18 is less than 0.2, so you need to select this one, right? You select D, and D require 0.18. So the idle time of the workstation, the remaining time of the workstation is 0.2 minus 0.18, which is 0.02, right? And if you move 0.02 here, the eligible task still, okay? You delete A, you delete D, right? E cannot be started because E requires C. So the eligible task still B and C. And because B and C, the operation time for, or the task time for B and C is more than 0.02, right? The remaining time of the workstation, so you cannot do anything with this workstation anymore. So you close this workstation, you close the first workstation, and then open the next workstation, that is the second workstation. Whenever you open the new workstation, the available time will be equal to the cycle time here, that is 0.4. And the eligible tasks again here, B and C, right? B and C. And then which one you select, which one you will select, which one you will select, depending on LOT, because B is greater than C, right? Okay, task time B of B is greater than task time of C, and 0.37 could fit in 0.4 here, right? Okay, you need to select B, and the remaining time is 0.4 minus 0.37, right? Okay, so the remaining time is 0.03. And the eligible task, now delete this one, delete this one, E cannot be started, F cannot be started, right? Eligible task is just C, but C, the task time of C is more than the available workstation time. Okay, so you cannot put any more tasks in workstation number 2. So you close it, close workstation number 2, and then open a new workstation, that is workstation number 3. Again, the cycle time is reset to 0.4. Now just only one task available for you to choose, that is task C, which require 0.21. So eligible task is C. Select C. When you select C, the idle time or the remaining time of the workstation is 0.4 minus 0.21, which is 0.19. 0.19 will be moved to available time. And then once you add task C in workstation number 3, right? Okay, this one you have already done this one, so E could be the eligible task, but not F, because F require both B and E. E still didn't done yet, so in that case F cannot be started, so the eligible task just only E. So in this case the workstation time, available work time is 0.19. E require 0.19 also, so in that case it perfectly fit into the workstation. So you add E into the workstation number 3. So the remaining time is 0.0. So 0.0 it means that you cannot add any more tasks. So you close workstation number 3 and then open workstation number 4, right? Available work time is again reset to 0.4. Then coming back to here, once E finish, okay, now F can be start because B already finished, E finish, both finish, F can be start, right? F require 0.39. F require 0.39. So 0.4 minus 0.39 is 0.01 idle time, right? You can put 0.01 here, and then the next available eligible task after F finish is G, right? But G require 0.36, which is more than 0.01. So you cannot fill G in workstation 4. So you have to close workstation 4 and then open the next workstation, that is workstation number 5. Again, the cycle time is reset to 0.4, and the only one task that you can select, okay, that is G, that is the last task, and G require 0.36. So you select task G, and the idle time of the workstation is equal to 0.4 minus 0.36, which is 0.04. This is the way that you will allocate tasks to workstation. In this case here, NA you can count from the number of workstation that you have done here. So the maximum number of workstation, okay, or the actual number of workstation is equal to 5. 1, 2, 3, 4, 5, right? And workstation number 1, the task that will be occupied in workstation number 1 consists of A and D, right? You put A and D, and the time required to complete the task, these two tasks in workstation number 1 is 0.38. 0.38 come from A and D, right? A 0.2, D 0.18. Okay, the total is 0.38. And then workstation number 2 is task B, right? Task B here, workstation number 2. Task B require 0.37 here. Put, okay, this is workload for workstation 2. And then workstation 3, C and E, right? Put C and E here. Workstation number 3, C and E require 0.21 plus 0.19, so it's equal to 0.4. And workstation number 4, okay, F, just only one F, require 0.39, put here. And the final one, station number 5, you put G here, put G here, and the workstation time of workstation 5 is equal to 0.36, right? Okay, so in this case you get 5 actual workstation, NA is equal to 5. If you remember the theoretical number of workstation that you have calculated previously, equal to 5, right? Okay, theoretical is 5, and actual, okay, actual is still 5. In reality, the actual number of workstation must be equal to or more than must be equal to or more than number of theoretical workstation. So if in your assignment your NT, suppose your NT is equal to 5 and your NA is equal to 7, okay, it could be possible, right? Or your NA is 6, it is possible. But your NA, if your NT is 5 and your NA is 4, in that case your calculation is wrong. Alright, okay? And in order to identify the bottlenecks in the system, okay, this is the flow chart, right? Consists of 5 workstations, 1, 2, 3, 4, 5. Raw material come this way, past process number 1, process number 2, process number 3, process number 4, and process number 5, and coming out as a finished good here. And the bottlenecks of this line is equal to the workstation, is equal to the cycle time of the workstation, the maximum cycle time of the workstation. So here the cycle time of this workstation is equal to 0.38. This one 0.37, 0.4, 0.39, 0.36. So the maximum cycle time of the workstation is equal to 0.4. Okay, comparing to the other 4, right? Okay, so this one is the highest cycle time of the workstation. So this workstation is the bottlenecks, and the cycle time of the bottlenecks workstation will be equal to the cycle time of the whole line. Okay, the whole line will be controlled by this workstation, and the cycle time of the whole line is equal to 0.4. Alright, okay, so in this case NA, actual number of workstation, is 5 from the line balancing table, and the efficiency here is 1.9. okay, 1.9 is the summation of task time divided by NA 5, okay, actual number of workstation, and divided by the cycle time of the line. This 0.4 come from here, the cycle time of the bottlenecks workstation. Okay, 0.4 here is 0.4, right? Okay, which is the efficiency, actual efficiency of the line is equal to 95%, and the balance delay is 1 minus efficiency, that is 1 minus 0.95, which is 5%. Alright, okay, balance delay 1 minus efficiency, balance delay of the actual is equal to 1 minus efficiency of the actual line, which is 5%. So okay, so for this presentation, I would like you to do the assignment, which is quite similar to the midterm examination. I would say that the assignment, the company operate 1 shift per day. Okay, suppose the 1 shift consists of 540 minutes with 1 hour lunch break. So in this case, don't forget to deduct lunch break to get the available work time from the 1 shift here, right? Okay, and this company produce the product that need to be produced by this assembly line is 960 product and need to be complete each day. And this is the number of tasks, 7 tasks again, time required, and the new precedent relationship here. So I would like you to draw the precedent graph. This one, you need to draw the precedent graph like this, okay? But because of it's changed a little bit here, so the new precedent graph will be redraw. And find the theoretical cycle time theoretical number of workstation, right? And then balance the line using LOT. You need to prepare the table, this table. Okay, need to prepare this table, and then find the bottleneck workstation and draw the picture of the line. The picture of the line is like this. This is the picture of the line. Okay, the picture of the line. I would like you to draw this one, and then find the actual cycle time of the balance line. So the actual cycle time, you need to find the bottlenecks first, and then the cycle time of the bottlenecks workstation will be the cycle time of the line. Alright, okay, that's all for me for this week. Thank you for your attention. See you next week. Bye.